Welcome to today's Accendo Reliability webinar. Today I want to talk about success testing. And you may know it by other names, and we'll get into what I'm talking about here. Yet it's a common approach um, for reliability testing, and you could use it for all kinds of things. Yet it's pretty economical, so it seems to get attention that way. Yet I find the application includes people that ignore some of the assumptions and the risks that come involved with it. So I want to dive a little bit deeper into the ins and outs of how to set up this style of testing. And as you know, we do a lot of testing, and I've often said, and I advocate that it's a last resort. It's expensive, it's time consuming, there's uncertainty around it with whatever kind of testing we do. If we're using a sample, for example, there's just sampling error that adds a layer of complexity that do we really need? Yet we do a lot of testing, and it's because that it's tangible. The folks we're working with and work, will believe a test result more so than a simulation. And even though our tools and techniques are getting better and better, we still need to actually drop our product and see what happens to it. We may have used finite element analysis to say, yeah, we have a solid design, yet we want to verify. We want to make sure that the all the work we did in simulations and engineering and design for reliability is actually true. And to some extent, when there's lots of testing that we do in order to make sure is probably the best excuse I've ever heard. Yet it's expensive. We get samples, we take engineering and technician time, there's capital assets involved with applying stresses of one sort or another, or controlling the stresses. And then there's measurement systems, and then there's analysis. And then it's explaining what it is that we did so that other people can interpret it and understand it correctly. It is expensive. And it's one of the barriers that I hear often from folks is that I don't have enough budget or samples to do adequate testing. And speaking from a statistician's point of view, and somebody says they want to do 99% reliable with 5 nines confidence in it or something like that, and then you tell them you need a couple 100,000 samples, and then they back off being so persistent on what criteria they have. Yet it's a balance, right? If we really, really need to know, then we're going to have to pay for it in one way or the other. And some test systems are more expensive than others. And of course, it depends on your product and industry and so on. Yet what we really want is that the evaluations we do, the experiments we do, the testing we do should actually produce information that we can use to make decisions. And that's what I call is a value. We're going to invest, say, $100,000 for a test suite, and we better get useful information out of that would be informative to somebody making $1 million decision, kind of considering a 10-to-1 ROI. If somebody's trying to make a decision that would only affect $10 worth of our product or have only that much influence one way or the other, then spending 100K to get a $10 return is probably not useful. And I hope many of you already intuitively understand that. But the idea is that we have lots of options to add value, and testing is one of those. And part of it is, well, how do we get the right balance of accuracy and precision and confidence and sample sizes that we have available versus what we would really like, and so on and so on. And so success testing is one of those that allows us to test products using the binomial theorem of pass fail with 0 failures. And it typically, just on the binomial and compared to other types of testing, with few exceptions, is pretty economical in meaning that it uses the fewest samples. Now, it's still an expensive test depending on how you set it up and what stresses you apply. Yet it tends, if you want a little bit more precision in the testing, then you allow it to have failures, but then you need more samples. And so we'll talk about some of that. So any of you do this where it's called success testing or zero failure binomial test plans, that kind of stuff? Is this something familiar to you? Because I should probably just check my assumption that you've seen it. Yeah, Bert's got it. Okay. Yeah, a couple of folks are chiming in. It can be a demonstration test. Yep, it can be. Exclusively. Oh, well, John, we're going to have to talk about that. But if you do it well and it works, that's great. All right. All right. The problem that we face is that somebody somewhere in our programs and products development and factories and everything else is going to say, hey, will this work long enough? We created an item of some sort or a system of some sort, and will this work for, say, 2 years? And let's say it needs to be 90% confident over 2 years. Well, we don't have 2 years to run a bunch of samples, so we probably would accelerate it. And I think that's my next slide. But this is a very, very common question is, will this work in our customers' environment or in the way they use it? And that's part of, I think, Yes Waneth, I think, I'm sorry if I mispronounced that, demonstration test is basically take the whole system and this is where I see it most commonly, is you take the whole system and you operate it either right at use conditions for a duration that you and your customers agree is sufficient. And if all those samples pass, then you can say with some confidence that it's reliable over that duration. And it's not uncommon to do. And there's some nuances and tricks in this, but the statistics are pretty simple. If I have a handful of samples that the formula says if I run those for the equivalent of a lifetime, I'm getting ahead of myself a little bit, but I'll come back to it in more detail, then we can say with some confidence that the reliability is at least some value. And in general, it allows us to say, well, we have evidence that it's good, which is, something that we're commonly looking for. And people like tests that pass. I think it was part of our schooling in so many different cultures is that the idea is to pass the test. Whereas, as many of you know, I really like tests that create failures. It does so much more for us, and we'll talk about some of that a little bit later. Yet I like getting failures. It answers so many questions and challenges so many assumptions that it allows us to be more certain, not confident, but certain that our test was able to do what we thought it was going to do. It created a failure when we thought it would create a failure. And yet that's in general more expensive to do, needs more samples to show a particular confidence over some reliability term. And people in general, the folks we work with, I had one engineer tell me, he says, you don't understand. You come in here and you talk about failures all the time, and it's the failure rate and so many problems and the failure mechanisms. And I just want it to work. I want it to be successful. So we came to a compromise. Instead of me saying it has a 2% failure rate, I would say 98% reliable. And he was happy with that. It's just that we come at talking about the performance of our products, usually from a failure side of things. And lots of other people we work with want to talk about how many are going to be successful. Two sides of the same coin, I know, yet it's a common question. How many will survive? And will they enough survive that it's a viable, that we meet our goals or objectives. So I'm sure all of you are familiar with this question in one form or another. The issue is that I was working with a medical device company a few years ago, and it was a syringe type device and a lot of molded parts, and um, they were measuring dimensions and interfaces and making sure that the syringe would, push out the right amount of medicine and by volume and so on. So they were really trying to pay attention to leakage and seals and stuff like that. And they could get hundreds and hundreds of samples for a relatively modest price. Now, it really did take time to make all the measurements, to make all the testing and measure all the pressures and so on. Yet they felt that it was necessary for them to prove to the FDA and to their potential customers that their product was going to work as expected. And the dosage was important so that they were paying particular attention to all the elements that affected how much medicine was administered with their device. Yet it's rare that I ever run across a company that say, oh, I need 850 samples for this part of the test and another 800 or 900 samples for this part of the test, and so on and so on. That is pretty rare. And in most cases, I'm thinking of, say, like a laptop, I'm not going to get 1,000 laptops to go make measurements and test and evaluate and so on. Not likely that that's going to occur. And even though we're going to sell millions of them, the chance that you get hundreds and hundreds of samples is, in my experience, has been very rare. So we almost always face the samples that we have available being limited. Plus, any of the prototypes that we're dealing with on a team have lots of other priorities. The salespeople want them to start demoing the product and getting feedback and excitement with their customers. The software team need it as an actual device they can run and evaluate their software. Yeah, and Rochelle was talking about we can get two samples. And like, you know, statistics is a bit difficult when you have two samples. Um, Technically, you can calculate an average. Um, I don't think standard deviation would be all that useful with that kind of stuff. And then doing anything more sophisticated is really difficult. And Rochelle, we've talked before, yeah, with only two, yeah, we're just going to have to do halt or break it of some sort, or have a very good evaluation technique with it. Yet at the end of the day, when we say we want to demonstrate or prove our system is good, somebody should say, well, how many samples do we need? Well, that's a relatively simple question. My flip answer is always more than you're willing to allow. And it depends on, well, what do you want to achieve? What test result is sufficient to show that you're good? And that's where we start talking about confidence and reliability, and hence the binomial zero failure approach. Part of it, though, is that we like testing, right? We could say, based on historical data or on a system model and looking at key failure mechanisms and so on, that we're good. We have a 90% reliable with 90% confidence, and here's the evidence, and or whatever our results are. And they may say, well, where's the testing? Is some people just want the testing, and sometimes we do too, because we know that there's things on the interfaces between, say, the power supply and the CPU or hard drive and so on, that certain combinations act differently than others. Now, if I only have a sample of two, it's really hard to pick up on all those unknown variations. Yet, doing a tangible test allows us to evaluate a system, for example, for failure mechanisms we may not really understand, we didn't know existed. And if we can operate it as a demonstration, say representing a year of use, I remember Carl talks about a car door machine they had that would open and close the car door. And they would replicate what they estimated be a high percentage of users or people using the car doors and how often they would open and close it over some period of time. And there's all kinds of issues with having a robot open and close your door for you. None the least of is that it's always the same. And in some systems that may accelerate the wear mechanisms because it's always the same. In other cases, it has no lateral forces. It doesn't represent real use. Um, I know as a 4-year-old that the door was actually a nice, surrogate for a playground. I would just swing on the door. Now, not that I weighed all that much, and hopefully the door didn't get bent because I did it. At least my parents didn't tell me. Yet the idea is that use conditions are often with lots of variability. And setting up a test that mimics use conditions is tricky to do in most cases. And yet we still want to test. And it may be contrived or controlled or at fixed temperatures or fixed loads or whatever. Yet we feel better, and some of the people we work with just have a gut feel that that's better than any of the other techniques we use. And then they match that with, well, you don't get enough samples. So what are our options? What do we learn from that? So at that point, it comes up that, oh, we want to do a test. We're probably going to be limited on samples. How do I set that up? And that's the topic of today is the idea is using the binomial distribution and set it at 0 failures. So what's the chance of flipping a coin one time and I get a heads on a fair coin? Well, it's 50%. We don't need a calculator to sort that out. What's the confidence of that? We could, it doesn't really come into play until we start doing more samples and we're doing it 10 times. What's the probability that 22 coins will land on a heads with a 90% confidence? Well, I don't know. I'd have to sort it out, but I don't think it's very high. So the chance of us passing a 90% confident test with 90% reliability that we only get heads with a 50% failure rate is probably pretty low. Now, we hope our product is not a 50-50 chance. And we're maybe saying we want it to prove that it's 90% reliable over a lifetime, and M is the lifetime. The idea is that if the actual product's reliability, the part we don't know and we're evaluating, is say 95 or 98% reliable over a lifetime, taking a sample and subjecting them to the same or equivalent forces and stresses and so on to represent a lifetime, then we could evaluate with some confidence that it meets that criteria. And so I always use 90% confidence or 90% reliable because I remember the outcome. I don't have to get my calculator out. So in essence, if I take 22 samples, it's 21 point something and you round it up and run them for a lifetime. And let's say it's a door latch. And so we have some number that we estimated or calculated or measured that represents a lifetime of opening and door closing cycles. And we want it to be 90% reliable with 90% confidence. If the door opens and closes, the 22 sets of doors open and close for whatever that number of that represents a lifetime, and it passes. At the end of that test, the doors are still operating, they're still in spec, they're still doing what they're supposed to do. Then we could say that we have a 90% reliability over that lifetime with 90% confidence. Doesn't mean we know the actual reliability. It just means that we have evidence that it's at least this much. Now, of course, if the actual door is actually at 90% reliable, it's going to give us a reasonable chance that one or more will fail because there's a 1 in 10 chance one of those doors will fail over the lifetime. And we've got 22 samples. And that's kind of a risky test if our product is actually at the unknown part is actually at it. So we'll probably fail that test. So the precision of this one is a bit speculative at best. And I'm sure there's ways to get around it, usually involving way more samples. But if the actual product is very reliable, we'll pass this test pretty easily. And the other piece of this is the confidence. I had a boss one time saying, well, we can go with less samples. If we reduce the confidence, the way this math works is that it reduces the number of samples we need. So what happens if I go to 80% confident? That's good enough, right? I says, well, that's a policy decision. You decide. So we reran the numbers, and I think we needed something like 18 samples or 15 samples. I don't remember the number. But if he said, oh, this is great. Let's just keep going. And this is this math. Let's go to 50%. And it really reduced the number of samples we needed. Wow, this is great. This is all math, this is science, this has got to work. So what's the issue with going to a 50% confidence? Gives me a chance to take a sip of water. I know some of you are statistically minded. Data sheets I often see for electronic components in particular, I see 60% confidence, and every now and then I see 50%. Why does that get you, at least for me, why is that troublesome? Yeah, close to 50-50, or if you use 50% confidence, 50-50. It pretty much, yeah, there's also a 50% chance it doesn't meet the target. Remember, confidence in statistics for the type 1 error is basically saying our sample that we're taking has some ability to represent the population's true values. So what is the real reliability? We don't know. We're taking a sample, and that sample will, if we only have one sample, it's going to be according to whatever distribution we're pulling from, what's the likelihood that it'll be representative of, say, the mean value. If I take the entire population, I don't need confidence because I just measured the entire assuming we have decent measurement system. I don't, confidence is irrelevant because I measured the entire population. And so the higher number of samples I use, the confidence part, whatever value it's set at, ends up being tighter and tighter and more accurate, saying, or we think is more accurate to say, this is where the true value lies. It's in some range. When it's 50-50, it's basically saying that you're going to get a result and it's 50-50 whether it's true or not. Yeah, and then Carl's putting in pretty much what I'm saying. It's the idea is that if we do a 50-50 confidence or 50% confidence, it's basically saying we don't know whether the results represent what the real population is about or not. It's a coin flip. And I often advocate that if you go down to 50% confidence, you don't need to run the test. If that's acceptable to you, just flip a coin. hopefully it's a fair coin, and you'll get the equivalent amount of information out of a test that's at 50-50 or 50% confidence. If you go lower, well, then you're pretty much just saying the results are very likely not representative of what we expect the true population to be. So numbers like 80 and 90% in 95, 99% are common depending on the policy of the organization. Don't be like my old boss that said, oh, this is just math. Let's just run this number way down and don't have to use as many samples. Well, there's a limit to that. Below 50%, it's pretty meaningless. And even 60% is you're going to get a rough, crude idea of what the result is. Now, if you only have 3 or 4 samples, that's a trade-off. How well do we really need to know whether it's an accurate result or not? We might not need to know. And which also questions why you're doing the test. Now, reliability, we have a goal. Usually for a product or a system, we say it needs to be 98% reliable over some duration. That's fine. It's a common technique to help align our organization and design a good product. Yet, if I put 98% in here, we need a lot more samples. And that's not really the decision. Remember that it's very difficult for this to say if it is actually 98% reliable, the unknown value, and we want to test it at 98%, it's very likely this test won't pass, that we will have a failure. Because the premise of it is that if it has 0 failures, then the test is valid that you can state that confidence and reliability occurred. And so if it really is, we expect and design to, and we have evidence from other modeling and systems that we really do, we think we have a 98% product, 98% reliable product. I would not test it at 98%. I would test it at, say, how bad does it have to be before we say we can't ship this? Let's say the question is it reliable enough to ship? Well, I flip that a little bit and say, how bad does it have to be when it's clear we cannot ship? Right? So it might be 95%, we need more samples. 90%, we need 22 samples with 90% confidence. So it's a way to reduce the target for the reliability and reduce your sample size to what's the decision point. What I found in practice is that if the product is actually 97% reliable and it passes this test, we're going to ship it, right? If we're testing it at, let me back up. If we really don't know that it's at 98% and we set the goal at 98%, it's very likely it will fail this test. If I back off to 95, it increases the chance that it'll pass. But that's only the math. The other side of this is the decision. If we pass at 90% reliable, and it actually is 97, it's a number we don't know, is that okay? Would we ship it anyway if we actually knew the real numbers, if it was at 97 versus 98? Now, oftentimes that's a trade-off, a decision. What's the increase in consequences of failures in the field, and so on and so on. The testing is not going to help you answer that question because through testing, we rarely get enough precision to know what the actual value is. Partly because we just don't get enough samples and among other things. The idea though is that at some point you're going to say, well, what if the actual value is 96%? Is that sufficient to say don't ship it, given that we have this margin of error and all these other problems? What if it's really 90%? Or we tested at 90% and we get a failure, that gives us evidence that we're not at 90% reliable or better. It's still got uncertainty around it, yet if we're farther away from the actual value, and we're testing it there, it's more evidence that it's at least that good or better. We don't know how much, but if it has a failure, we have more statistical power in the test to say, it really isn't 98%. It's much less. And it's not doesn't mean that it is 90% reliable. It just is less reliable than we would have liked it to have been. And of course, statistics works in weird ways. There is a percentage that you'd have a 5 nines reliable product and you're testing it to it. Is it at least 90%? Randomness is a fun thing, and it may have a failure in that test. And we can't conclude it's at least 90% reliable, 90% confidence. But the risk of that occurring is very, very low. And so thinking about this as the type 1, type 2 errors, and the bigger that gap from what we want it to be versus it needs to be where we make a decision, allows us to reduce the sample size in many cases. Now, I'm not at all sure if I've confused everybody. I probably confused myself a little bit. Now, the other element in this test is M, the lifetime. What in the world's a lifetime? Well, according to the binomial theorem and the way this kind of test is operating, I take a vehicle and it's supposed to last for 2 years on some racetrack, or let's do something that's actually shorter. Let's say it's a Indy 500 race car, and it needs to make 500 laps in some amount of time, hopefully fast. And on Sunday, when a race is occurring, that's one lifetime. And the really, really good cars, the ones that perform really well, are shaving that ability to do 500 laps with a very small margin. And then they basically rebuild the vehicle afterwards. And, they're changing tires as a balance between traction and weight and how fast they can change the tires out. And they don't want to go too far where the tire fails, but they also don't want to change the tire every lap. That would probably be a detriment to them. But let's say it's 500 laps as a lifetime. So we take a vehicle and we run it for 500 laps. If it finishes the race, that's it demonstrated that that vehicle can go one lifetime. And so we take 22 race cars, and if they all finish the race, then we could say with some reliability and confidence, there's some confidence that those vehicles have a certain reliability. Now we know that there's all kinds of failure mechanisms that can occur in a race, the mechanical and driver and interactions with the other vehicles. So it's unlikely in many, many cases to be careful what numbers you're looking to achieve. But I'm quite sure somebody's making those calculations. But a lifetime also allows us to do 2 lifetimes. And if I make M instead of one lifetime, which would be 500 laps, I make it two. It'd be 1,000 laps. I didn't change the actual reliability of the vehicle or of the product that you're dealing with. But if we can run 1,000 laps in an economical way, and this is important, make the assumption that that extra 100 laps doesn't incur failure mechanisms that just won't happen in the first 500. It may be a design feature that they only work for a limited amount of time and limited number of samples. And then we know that it's going to wear out. These things are going to change or fail. And I would say in a race car, maybe the brakes. There's probably some margin in there to go longer and go harder. Yeah, the clever mechanics that say, well, we can strip some weight out of this and we can change it after the race and so on, that the brakes may fail, say, at 900 laps. And that's not likely to occur in 500. So it's the issue of if you add more stress and add more stress over multiple lifetimes, then I get this mathematical benefit, you can use half as many samples or a quarter as many samples and so on, depending on how many lifetimes you go. The chance, though, that your product will wear out or have failure mechanisms unrelated to one lifetimes of use increases dramatically. And so I rarely, without fully understanding the failure mechanisms at play, advocate going anything above, say, 4 or 5 lifetimes. And even then, you got to really understand what you're doing and getting into. Now, the premise of the test is that if it runs for 2 lifetimes with this fewer samples and passes, it means your product was reliable enough for whatever your target was with that particular confidence. If you get a failure, and even if that failure doesn't apply to the first lifetime, you don't have 22 samples anymore. You have 21 samples, so you can no longer make the conclusion that you're 90% reliable with 90% confidence. So that you got to be very, very careful about reducing the confidence, setting how many lifetimes you're running, and focusing on what's the tipping point for decision for the reliability figure. Because there's a lot at play in just setting up this formula to figure out how many samples you need. And so I spent a bit of time on that. Hopefully, I didn't confuse too many people. And I know a handful of you use this formula or similar formula to do zero failures type of test planning. Did I miss anything? We've got a couple other things here, and then we'll talk about some of the risks. But what do you think? Is there any other ways to think through this formula or other considerations? All right. Well, I'll talk about some of the ones I run into all the time when I try to set up and run a test like this. Yeah, normal use definition, exactly right. And Carl's talking about the confidence intervals creation. Yeah, Bayes. You know what I found, Larry, if using a Bayes approach is that you do all the math around some prior and you do it on a binomial distribution, it saves you one sample. And so instead of 22 samples to do 90-90, I need 21 samples. And it significantly increases the complexity to explain why you need 21 samples instead of 22. And so I have not had the ability to explain why I need all this extra math and all these other assumptions in order to save one sample. Now, there are cases where one sample is I just only can get 21 samples, and then I would have to use Bayesian. I just find it extremely difficult to explain how the math works to other people, mostly because I didn't study or don't use Bayesian approaches very often. But I've done the math a handful of times, and it basically saves one sample. And if you get to higher and higher sample sizes required, it might save two. I don't find it really all that useful. Yet I agree that at some points it would be useful. Yeah, acceleration. Sometimes we just let's say it's not a race car doing 500 laps. It's a commercial or a consumer vehicle that's running kids to school or going for commuting or for whatever you do with your car at home. And we want it to last, say, for 5 years or 10 years. Well, we're not going to take 22 vehicles and operate them for 5 years before we launch the product. Now, some companies actually do long road trips and real use conditions type stuff in order to identify weaknesses that may appear over time. Some of us call that ongoing reliability testing. And there's variations of that, but it's rare that it's in use conditions for the full duration if it's longer than you can do in a day. So we may use one or more acceleration models to replicate a one lifetime or a lifetime of use. And I use the door testing as an example. Let's say a door would be open and closed 100,000 times over its lifetime, however we came up with that number for a particular model. Well, if we open and close that door in a lab a whole bunch of times and just count them until we get to 100,000, then check to see if it's working or not, we could do that much, much faster than, we open the door, go to, close the door, go to school. Open the door, let the kids out, close the door, and go to the grocery store, open and close cycle there, open and close cycle when we come back, go pick up the kids, open and close cycle. I just talked about 6 or 8 hours worth of use, and we open and close the door like 10 times. That's it. That takes a long time in real use, yet we can do it faster. It's a very easy, common acceleration model if you have that opportunity just to go through the cycle more often. And there's downsides to that. And this is the simplest one to explain to somebody. Well, the door typically gets open and closed 10 times a day. We'll just do that within 10 minutes until you realize that there's no debris, there's no creep because we're going too fast. There's no um, uh, rust or corrosion. It's we're going too fast. There's no salt fog. There's no lateral weights or pressures or stresses. There's no misalignment. There's a whole list of things that affect how long a door opens and closes successfully that in the lab, if we're just interested in it opens, it closes, and we do it repetitively using a mechanical device that just does it. We do that with buttons a lot of times. We get a little pneumatic finger basically that just pushes perfectly on the button and releases it and does that many, many times. It gives away or it eliminates some of the variability that occurs in real life. Now, in some cases, that's acceptable. We can get the test done quicker, yet we know that it's not a complete set of what actually happens in the field. And sometimes we make that trade-off and say that's okay. If it's a chemical process, some people will say, well, we don't really know the Arrhenius equation's activation energy for that particular process, so we'll make an assumption. And depending on what that assumption is you may be way off and never pass this test, or because it accelerates it way too fast, or vice versa, that it will never fail, but we don't really know. We don't have the details to check that model. And the more complicated the acceleration model, say using multiple stresses or very high stresses or combination of all those things, it complicates what actual failure mechanisms are at play. And so it's one of the ways that we commonly use this equation is to say, well, we can accelerate it. So one lifetime can be done in weeks versus years, for example. It increases the amount of test uncertainty that does the set of stresses and the activity we're using work or not work. And I agree with you, Bert, is that you really do need to know the dominant failure mode. I would say failure mechanism, right? If we know that it's the doors fail because of misalignment over time, bolts extend, different material creeps or deforms with time. Let's just assume that that's the issue. And I don't know for sure. I'd have to talk to Carl because he grew up doing door testing, I think. The idea, though, is that if we know exactly what causes it was the dominant way our door fails, we can design a test that uses stresses that accelerate that set of mechanisms. And the other ones are insignificant, so we don't have to worry about it. And so the idea is that if we understand it really well and can focus our acceleration on that and have a really well thought out and and verified acceleration model, yes, it's a great tool to use. The trouble is I see people take a box, say an electronic box, and they throw it in a chamber and they say, well, we can go to 85C and it still works, but what's our acceleration on the whole box? Well, what's your failure mechanism? Well, we don't know. Okay, let's take a look at your box. You got 1,000 components in there, and you probably have 80 or 90 different, maybe more materials in there. Um, did you do an FMEA? What's the most likely thing to fail? Okay, well, that's a mechanical thing. That's a push button on the front, or it's a user error where they push the wrong button on the screen, or somebody spills something on it. Maybe that's from your field history. That's the most common problem that you have. How does a hot chamber replicate any of those things? So you really need to match the stresses to hopefully your dominant failure mechanism or a careful understanding of how the product is used. And the more types of stresses you put on it, say high voltage and vibration and temperature with a periodic, well, it's ramp it up and down to do a thermal cycle. Now you've got an extremely complex acceleration model to sort out and figure out. And the further you go away from actual normal use conditions, the more assumptions and nuances and considerations to come into play, and probably the further from accurate you are. So this part is often underestimated of how complex it is. And so be very, very careful as you set up accelerating your device to use this formula, or any accelerated test for that matter. At some point, we're just not going to have enough samples. And if you really need to know it's 90% reliable over or with a 90% confidence, and that's the criteria where you need to make a decision, and you don't have 22 samples, well, there are some other ways to go about doing it. If, only if you really understand the failure mechanisms and what's the dominant failure mechanism you really care about. If it happens to be degradation, then you may be able to use that with fewer samples and get enough time to failure sets of results that you can then estimate a distribution and solve the problem. Of course, the fewer samples you have, the more unsure you're about the confidence is difficult to maintain. Yet some cases you can do that. Other cases is you go, well, we have really, really good models. I'm thinking of an aircraft wing. We have all this wonderful research and modeling about how far this wing can bend before it snaps and how much load it can withstand before it fails. And then we take one wing and we test it to failure as a way to say our estimates, our simulations were right on target or were conservative. And then we have some evidence. We don't have anything statistical. We have some evidence that it behaved as expected, as the model said. But with very, very few samples, you need a really good understanding of the failure mechanism and modeling to compare that one sample to. So there's rarely a free way to get at understanding the unknown actual reliability of your system. Some argue, and myself included, is that even in the field, we don't know about all of the failures that occur. Some people just don't buy your product again. Yeah, field data is good. It's better than most other approaches to it, yet it can be noisy. And so it's something to do. Stress strength relationships, I've seen that done before as a way to minimize your number of samples. I would rank that as part of doing the modeling, whether it's stress strength or it's finite element analysis where the stresses go and when it exceeds the strength of your system, on and on and on. There's so many different ways we can model and simulate our systems that And it's getting less and less expensive to do because of the power of our systems these days. Like anything else, though, it has to be done well. And running a test is a way to make sure it's working. But let's say we create a beautiful test and we run it. What could go wrong? Save this for the last few minutes of this thing. There's always risk in any failure we do. The biggest risk in this is that you get a failure. We have 22 samples, and we all agreed that if they pass, that means we have a 90% confidence that we have a 90% reliability. And one of them fails. It doesn't matter why it failed. It's not working. Remember, it's a binomial, right? If we flip the coin and it comes up tails, we've defined that as a failure, and we got a tail. So it failed. The product doesn't work. The green light didn't come on. Whatever we qualify or quantify prior to the test is what is passing. And I think Bert or somebody else mentioned earlier is that sometimes that leads to a whole discussion of what it means to pass the test. So the idea here is that mathematically, if one of those 22 samples fails for any reason, you cannot conclude that you have 90% confidence with 90% reliability. You don't get to conclude that. Now, you could be clever and say, well, what if we say it's only 89% reliable with 90% confidence? The test is not, it's not a floating process. If I can change the conclusion based on the results, then our test is not valid. The approach, the way I understand it, the approach for binomial distribution testing is that that's your hypothesis. If you get a failure, that means you cannot draw the conclusion the test was designed to do. It doesn't, it means that the test failed or it passed, whichever it did. It's binomial. There's no middle ground. There's no fudging it saying, oh, it's really only 98% or 88% confidence. That might feel good, but it's a problem with the way you design and set up your tests and the underlying assumptions in the test design, especially as binomial. So part of this is that if you really wanted 88% reliable with 90% confidence, then set up and design the test that way, right? Now, there are a few options that if you do get a failure, is if you keep running the test and you get another failure and then you get 5 failures altogether, well, you got 5 failures and what's that, 17 or so sensor data and do an analysis on the time to failure data you have now. It doesn't mean that, and you don't know when the test is going to end because you need some failures. One's not enough unless you have lots of other prior data. The idea is the the test itself, the success test signaled that it failed. And you don't put a new product in to run out the amount of time. This isn't assuming that it's a constant hazard rate. No, those are two different products. You can't add products and hope it runs. That's kind of, I could do that all day long, and eventually I'll find 22 samples that will pass. Well, that's not very useful. That's not real world. That's not giving us the conclusion we're looking for. Yeah, Larry's jumping in on let's see, I'm trying to keep up with some of the comments here. Um, yeah, a finite element model, creating a confidence interval for that. Remember, the models are trying to replicate the population. They're not a sample. And so those things, they're not taken into the account of the variability. It's usually as designed, or we might use worst case, the weakest steel and the highest loads in the model. Those kinds of things try to replicate It's a good question. I wonder if you could do it. Is if you understood the sources of variability and modeled it appropriately, that might work just fine. I would use like um, I'm just thinking out loud here. I would go at it with a Monte Carlo. If I understand the various distributions of the elements that would significantly affect the performance of our system, then I would use those distributions to populate and run various models and see what kind of distribution you get out of it. It's an interesting question. Larry's talking about that, using field data is very valuable because the customers and environments and the uses doesn't change much from one family of product to the next. Well, that's until you give an iPhone to your 12-year-old daughter, then the usage and environment changes dramatically, usually for the worse, but that was years ago. Um, so comment here is that the failure occurs, the other samples are suggested to increase test count. If they pass, does that still pass the test? No. The hypothesis is that 22 samples need to pass to show what we have. And adding another sample now means I'm actually testing 23 instead of 22. So I've changed the premise of the test. If I change the goalposts, well, then why did I run the test? Let's just pick whatever goalpost we want. If I, run in the obvious one is if I replace and run for the full duration extra samples until I get 22 that failed, hopefully that's clear. That's not showing us anything other than we're clever enough to have plenty of samples after we couldn't get even 23 before. Yeah. In adding more time is effectively saying that you're changing the M value, the number of lifetimes. So instead of 1, it might be 1.2 or 5 or whatever number it goes to. But that's the same as adding more samples, right? It's replacing the bad ones until you get enough that failed. Now, if the test was set up as I'm drawing a blank on what it's called. Um, there is a test approach where if you have, it has two thresholds. If it runs long enough without failures, then you know you've reached the goal. If it has enough failures quick enough, then you know you didn't reach your goal. But it's a sliding scale. There is a possibility that it could run in between those. It has a failure just before you would have proved it's good, or it runs long enough that it's and that it I want to say PSR. Oh, Larry, you know what this is. Instead of doing a simple hypothesis test or a success test, it's a combination of time and success that allows you or failures that allows you to make a decision. Is it good or is it not good to some criteria? And I'm drawing a complete blank on what that's called. Sequential probability ratio test. Exactly. Thanks, Larry. I knew you'd know that. If you set up a test to do that, then sometimes running longer is all you need to get past a few early failures. The risk is that it's not conclusive. You can finish the duration that you planned for the test and you still don't have an answer. Or it may take an extraordinarily long period of time. Also, the zero failure binomial is usually more economical on the number of samples you need to show the same confidence and reliability target. So that's why the success testing is usually the go-to one because it's pretty what do they call it? Economical. I'll use the word I can pronounce. FEA, generate continuous stresses or strains rather than discrete varying paths. Yeah, the FEA tools are getting really good, and working closely with the folks that are setting up those things is I advocate going to, well, age your product, age it for a lifetime and then see how it performs. If we know how that material changes over a lifetime of stress, or how the circuit performs or the software performs, whatever, that can get tricky. Yeah, we can do it. let's see. Is jamming a failure mechanism where I don't have to worry about monkeying around with a lifetime parameter? John, I'm not really sure what you're getting at there. Yeah, let's see, I've got a few seconds left. Let me bring up my next slide, which is pretty close to the end. I talked a lot about acceleration. If it's unrealistic, we can over or under accelerate it, and then our results are unknowingly inaccurate, and that can be a real problem for us. And then sometimes we just miss the stress. The things that accelerate or cause failures in the field are things that we just don't include. One of my favorites is dust. If you have a cooling system if you have a fan on the side of your box and you're not putting dust in it, or debris or carpet fiber, or, that kind of stuff, you're not changing the ability for it to transfer heat. And the test is missing that stress. If you're only doing it heat and it's a clean chamber, that may be very important. So we'll have to do it. Thanks, Eshwan. We'll talk to you later. All right. We're coming up right in the end of this. I think I've got, hopefully I really stressed, no pun intended, that yeah, it's a relatively simple formula. It's in common use, yet there's a lot of work that goes into getting it right. And to be successful with it, both in informing the people that need the results so that they know what information they're actually getting, rather than, oh yeah, it passed, because we certainly can set one up that will always pass. Just don't stress it very much, and then don't work it too hard. Don't turn it on, those kinds of things. There's games we can play with when we have a failure. You have to think that through, what is the statistics and the background of setting up that test? What's the set of constraints and assumptions that we're making if we go retroactively and change the parameters of what we're trying to accomplish as we find more information? It's usually not, there aren't very many good options if you have a failure in one of these tests. And finally, it's a common practice, so we really do need to think about it. And as Chris Jackson would say, you really cannot check your brain at the door. Like anything we do, we have to think it through and really understand what we're doing. So with that, I'm going to say thanks, everybody. I'll stay on the line, but I'm going to go ahead and sign off here.